Hello everybody, I'm going to talk today about how reaction rate is affected by concentration again, except this time, unlike the last video where we focused on one reactant species, like the simplest case possible, I'm going to deal with two, or you can generalize this result from multiple chemical species today. So what we're dealing with is a reaction system where we have more than one reactant. In the general form of, again, these stoichiometric coefficients are written with the small letters, and the capital letters represent chemical species. We could write the rate law for this in terms of rate constant. I'm just denoting with R times the rate constant denoted K times the concentrations of the reactant species. We're focusing on the forward reaction, raised to the orders. I'm using the symbols M and N to denote the orders. I want to emphasize the point that there's no relationship between the orders M and N and the stoichiometric coefficients. Sometimes they're the same, sometimes they're not. Again, M and N we would expect to be numbers like zeros, ones, and twos. Occasionally, a half integer shows up. I will not put that on exams. And very, very, very rarely, the total of those will be 3. We call those are the reaction orders, or just simply orders. And then we also sometimes they'll talk about the sum, which in this case would be M plus N. That's called the overall order of the reaction. It's the sum of the orders, and that rarely, if ever, to my knowledge, exceeds C. It's typically, with the overall order, still 0, 1, and 2. So what we'll use is a problem taking ratios of initial rates. So what I have here is a typical example. This is in the aqueous phase. And the details of the reaction are not important, just to want to have one. The chloride ion, this would be a hypochlorite ion reacting with bromide, giving you the hypobromite ion and regenerating a chloride ion in solution. Pretty much just took an arbitrary reaction and put some numbers to it. It's at a certain temperature and it's doing this reaction that's observed under certain conditions. So what we have is a bunch of initial rates. So what we're taking is the rate at the beginning of the experiment, where you get, in a sense, the cleanest data. We're measuring it in terms of molarity per second. It must be a fairly quick reaction. And we have the molar concentrations of the two reactant species, the hypochlorite and the bromide, the bromine ion. And so we have different concentrations there. So we have different trials that we did with different initial conditions of the reactive species. So an easy way of solving this is using ratios. Take the ratios of the rates between two trials. Let's say the rate between trial 1 and trial 2 could be 2 over 4. So we take those two ratios, we have that. So we'll take the two rate laws associated with it and we'll make a ratio. And the rate constant will be the same. One thing I notice, I always like to simplify. We have 10 to the minus 4, 10 to the minus 4. I can just cancel that out. So I see here it's a 1/2, right? It's 1/2. 2 over 4 is 1/2. So I just chose to do trials 1 and 2. Now when I do this, I'm going to have the ratios of the concentrations of the species. Let's see here. We have ClO minus raised to the M, ClO minus raised to the M, and I'll put a little trial 1 and a 2 here, representing that that's for the different trials. And then we'll also have a multiplicative, or we'll have a ratio multiply that for the, let's see here, we got the Br minus raised to the N, Br minus raised to the N, and this is for trial 1 and trial 2. So we have that form. One thing to notice is, so we have here for the rates, we have a 1/2. I'm just going to write it as a 1/2. 2 over 4 is 1/2. Is that the bromide ions are the same concentration. So we, for them, can get a 1. Also, the rate, the constants K have canceled because they're the same. They're the same. So I just cancel them out. I try to keep it as simple as possible. So what we have here is the ratio of the ClO minus is going to be 0.0017 for trial 1 raised to the m. And then we have 0.0034 raised to the m. And then these two are the same. So I'm not going to worry about 1 raised to the n. It's just going to be a 1, right? So you can think of this as multiplied by 1. So right here what we have is this is the chloride ion concentration ratio. So if you look at this, this is, you convince yourself of this. This is the same thing as saying 1/2 is equal to 0.0017. That's basically, you can think of that 17 divided by 34. That's 1/2 to the m. Yeah, I do not need any algebra to solve that. That means m is 1, right? M is 1 here. So the order for the chloride ion is going to be Cl, just like that. It's going to be to the 1 power. We don't write a 1. That just looks very elementary. You don't want to do that. So it's raised to the first power. So we're going to have that in our final rate law. The goal here is to get the rate law. So let's do the same thing with trials. An easy way to do this is pick trials where something is constant. So we have here between trials 1 and 3, we have, what do we have? We have in trials 1 and 3, we have the chloride ion constant, but we have the bromide is the bromide ion is doubling up. So between trials 1 and 3, what's happening is we've got the rates are the same. The rates are the same. So when we take the trial 1 to trial 3, what we see here is the rate did not change. So that's 1. Again, the ratio, the rate constants cancel out. And in this case, we're going to get a 1 for the chloride ion. So the hypochlorite ion. So what we have is a ratio of 0.0017 to 0.0034. This is for the bromide ion, and that's raised to, we could call it, we'll make that the n, right? And so in that case, when you look at this, this is 1 is equal to 1/2 to the n. The only way you can get this to be 1, when you have 1/2 raised to the powers, n has to be equal to 0. It's 0th order. It's 0th order in the bromide ion. So that means that actually does not explicitly show up in the rate law. The rate law for this will look like this. Rate is equal to K ClO minus. And that's it. I mean, we don't write in the Br minus to the 0 because that's just 1. This would be the rate law for this reaction. If we wanted to know the units, and we have this is going to, rate is going to be in units of molarity per second. We're told that. And we have K, and then we have molarity here for the species ClO minus. It was measured in molar units. That means that K has to have units of 1 over S, 1 over seconds. So that's pretty simple. And that would be a good example of doing this type of problem, very testable. Could be in a long form or a short form problem. And the units are, again, I consider that one of the most important parts because that's just fundamental for all sciences. And again, one of the points here is that the stoichiometric coefficients on both species here are 1, just to balance it out. We did end up with a first order for the hypochlorite ion, but the bromide order is 0. There's no direct relationship when you have an overall reaction with the stoichiometric coefficients, which are both 1 in this case. By coincidence, it's the same here, but that's not the same as a rule. So on that note, we'll continue on to what I consider one of the more important topics, not only in this set of material, kinetics, but also in the course, and that's integrated rate laws. If you do know calculus, Although I'm not using it here, and you're curious where the mathematical relationships I'm getting come from, you can look in the back of the skill builder, and there's a little primer or a little, it's an FYI, strictly for your own information. If you're interested on where the equations come from that I'll be using, it will be, some of them will be derived using calculus. This is not a calc-based course, so you do not need to know calculus, but if you do, it kind of makes like where the equations at least come from more satisfying. So on that note, I'm out of here, and maybe I'll make another video later. Take care.